Hello, everyone. This is Spencer Snowling from Hatch, and I'm glad you've been able to join us today for our regularly scheduled monthly webinars about GPSX and the assorted features and wastewater content therein. Today, we're going to be talking about modeling inorganic precipitation with GPSX. And in general, I'm going to be talking about precipitation and the pH model and speciation of acids and so on. These are all things that are relevant to the sort of the inorganic part of the wastewater world that we try to model in our software. Okay, so I'm going to sort of start with a bit of an introduction and a bit of a background about how inorganics have been treated through sort of the history of wastewater modeling. So, from back in the day when it was hardly included in the models at all the way forward to what we're doing currently in GPSX. So I'll show you how we have come to model those inorganic components and where you can find out information about them in the software. And also, we'll talk about the relevant unit processes that are in GPSX that are relevant to controlling pH, to doing precipitation, either accidentally or on purpose. And then I'll go through some of the equations that we use and what the modeling approach is. And then, as always, I'll run a few desktop demonstrations just to sort of highlight the way that works in GPSX. And as always, I'll hang around at the end of the webinar today to answer any questions that you might have. So as usual, you can open up your GoToWebinar dashboard and look for the questions box and type your questions in there, and I'll see those coming up here as I go along. And then I'll wait till the end of the webinar and answer as many of those as I can in the time that we have together today. Okay, so to sort of set the context here, modeling the formation and removal of inorganic precipitates is a useful thing to actually include in your model. And the models actually capture that behavior reasonably well. And so they're a good tool to understand the inorganic side of your wastewater treatment. So certainly the inorganic components are a key element or a key feature of the influent wastewater stream. It's important to know information about them, both the soluble, concentrations of things like calcium and magnesium and so on, and also the inorganic portion of the influent solids that's coming in. It, of course, plays a big role and accumulates and becomes a significant part of your mixed liquor. So, and one thing that I know that people like to use GPSX for is to be able to study the circumstances under which we're going to have precipitation of inorganic solids, in places where they could be a real problem in the process. So specifically, we often like to talk about how struvite can become a nuisance at a plant. You can have it precipitate out in anaerobic environments under certain circumstances of temperature and pH and in influent constituents. And so, and I'm sure you've seen many pictures like this before where they can precipitate on the surfaces of the pipes. And then, of course, that builds up over time and it can significantly reduce the flow that is able to make it through that pipe, increase your operating cost. You have to spend more energy to pump through there. And then ultimately, if it's not something that can be either rehabilitated in place or you may end up having to replace some of your infrastructure. And when I was doing a little bit of background research for today's webinar, I came across a really interesting paper from, well, about 20 years ago. So the numbers might be a bit out of date, but it had many examples of different facilities and looking at the amount of money and effort that they were spending on battling struvite deposits in theirs. And it did have an example of a 25 MGD plant that was spending, close to $100,000 a year trying to control and trying to remove the deposits that were forming in their facility. The other flip side of that, of course, is that you can precipitate things like struvite. You can precipitate them out on purpose and do it in a way that you can manage it and collect it and sell that phosphorus as a fertilizer or some other form that is useful in some other thing outside of wastewater. So there are a number of companies out there on the market that sell technologies that can be used to precipitate out and remove struvite. to get at that phosphorus, to have it in a format that can be used as an input into some other aspect or some other field. And there are a number of companies around. Austera is a Canadian company producing the Wastrep process. There's a couple of American companies doing that, Multiform Harvest and Centresis with their Magprex, used to be called Airprex system. And there's a European company in Belgium there, Neuresis, and a number of other ones across the rest of the world as well, producing these things that they all kind of have a somewhat similar approach. Basically, these are fluidized beds where the very high concentrations of nutrients that are coming from digested sludge can come into this controlled anaerobic environment and allow for the precipitation of the phosphorus out, and then in a way that can be collected and separated from the water, which is then returned back to the plant, and you can collect the precipitated solids out and then sell those and have a bit of a revenue stream. Okay, so we want to be able to model those things properly in GPSX. So we need to know exactly how to correctly include those things in the model. So starting from way back in 1985, when the first activated sludge model came out, ASM1, it did not include any state variables at all for inorganic components of any kind. So I know this is a little hard to read because the font's small, but this is the matrix from the ASM1 model. And so if you are looking at it in sort of matrix format, the state variables are listed in columns here. This is the column for alkalinity, and it's about maybe the closest things you could get to an inorganic section. And really, in this case, it wasn't there to sort of model carbon dioxide or any of that sort of thing. This is really there as a sort of a stand-in for pH. So, but there were no precipitates, there were no functions to generate them, and there were no state variables to keep track of them and do mass balances on them. So in the very beginning, it was pretty much organics only. So therefore, in the very, very early versions of GPSX, the inorganic components were not really modeled explicitly. We basically made an assumption about the VSS to TSS ratio and the influent and various other parts of the facility, and then we just assumed all the rest of the TSS that was not VSS was inert material. So, and that's what it looked like way back then. So a little trivia there. That's what GPSX looked like when I first joined Hydromantis back in 1999. And so, so back then, yeah, there was you just worked with VSS to TSS ratios. So now moving forward in time, ASM2, and then of course ASM2D that came right after it, introduced for the first time a number of very specific state variables to handle inorganic compounds. So XMeOH and XMEP were metal hydroxides and metal phosphates accordingly, and they actually had state variables that were included in the mass balance of the model. So they were in the matrix, and there were rates to generate those things. They also included kind of a sort of state variable for TSS that kind of was not really adopted as an industry standard, but we did have rates for the consumption generations of these variables included in the matrix then for the first time. So in version 4 of GPSX, we added a new state variable XII to start modeling these things in a bit more of an explicit mechanistic way. Inorganic inert particulate, XII. And it continues through in GPSX to this day. So it is, I guess you could call it a catch-all sort of inorganic particulate state variable for any sort of silt or sand or fines, precipitates, anything else that settles in the wastewater that doesn't have COD and that is not already one of the other state variables. So basically, you'll find that there will be a not insignificant amount of this in your influent, especially if it's in a large collection system where it's traveled some distance to get to the plant. It'll pick up a few things along the way. And then this is treated like any other state variable. It's mass balance, and we integrate it across the entire plant, and it makes up a significant part of the solids, as we'll see. So, and of course, in the actual matrix, its rate is 0. There is no, there's nothing adding to or subtracting from it in terms of the biological processes. Now, we get from that information that we have to TSS by using the COD state variables and the other inert materials via our composite variable calculations. So you can read all about this in the GPSX technical reference. There's large illustrated diagrams that kind of show you how we go through the process of calculating all of the composite variables, concentrations like VSS and TSS and so on, in the concentrations menu. But the short version of it here is that we take all the particulate COD components, and then we have ratios that we multiply them by to get us to VSS. Each different type of COD has its own ratio. And then ISS, the inert suspended solids, is made up of XII that I was discussing earlier, plus all of the other precipitates. And we sort of add those two things together to get TSS. So properly calculating this, making sure that we understand and model the inert side of the equation is also just as important as modeling the other side of the equation, the biological part, where we want to make sure we calculate and grow the right kind of biomass. So as a next update, GPSX version 6, which was released in 2010, so more than 10 years ago now, when we first released the Mantis 2 biological model, we stepped it up to that next level of sophistication in the way that we modeled the inorganic. So when we went from the old ASM models into our own in-house supermodel, that's when we introduced a much better way to go about modeling the inorganic precipitation and so on. So now we have state variables for many different kinds of inorganic compounds, both soluble and particulate. We have the precipitation and redissolution reactions in the model matrix itself. So any place that you see biological activity happening, buried in that is actually the precipitation and dissolution reactions in there as well. So we have speciation of all dissociating compounds, and we have, and since we then have concentrations of all of the charged components, all the ionic components, we can then do pH calculations at every step of the way, all the way through the plant. And so if you've ever used our pH model, that's that step forward that we did when we introduced the Mantis 2 model. And then since that time, we've developed new models, new unit processes that focus specifically on inorganics removal. And I'll talk about a little bit about those towards the end of the webinar today. So if you go to any place in your model, so right-click on a tank or right-click on any connection point, and go to the concentrations menu and scroll down to inorganic variables, it's towards the bottom of that menu, you'll find the soluble inorganic state. So here you'll see things like, soluble calcium and magnesium and potassium. And then we also have these other things here called the other cations and other anions. You can define all of this in your influent. We have default values that are typical for North America, but maybe you happen to be in a place where your water is a little different than that. I've certainly talked to people who have done modeling with GPSX in places where they have, very hard water, and so they have very high concentrations. Other places where maybe they don't. I once talked with a really interesting conversation at WEFTEC with somebody who lived in Hawaii, where they have all of their groundwater is not affected by any sort of dissolved salts so much, and so it was really interesting to talk about how their water was different than ours. So you have all of these components here, and also total soluble inorganic carbon, which is also another inorganic component. This is the one that's kind of controlled by your influent pH and alkalinity. And we then also have all the particulate inorganic state variables too. So we have the inorganic inert particulates, that's XII, the one that I mentioned before, and then all of these precipitates here, aluminum hydroxide, aluminum phosphate, et cetera, all the way down here, and struvite is down here at the bottom. So those are all there. They're all present. We're mass balancing all of those different types of inorganic compounds all the way through the whole plant. Now, any place where you get to a unit process on your drawing board where there is a regular bioreactor happening. So these ones here that I'm showing, the regular CSTRs and STRs, SBRs and so on, oxidation ditches, any of those biofilm units, anything that has biological equations in it, you are also going to see the precipitation happening here, potentially, if the circumstances are right. And of course, that also includes the digesters, the anaerobic and the aerobic digester objects. They're also that regular biological model happening. So that's how we allow for the formation of struvite, is because it's included in the biological matrix that's being used in the anaerobic digester, and we mass balance that growth or that removal of phosphorus and everything else alongside the growth of the biomass and gas generation and everything else. There are some units that can allow you to sort of deal with the inorganic part of the waste stream in a little different way than the regular biological part as well. Our clarifier models often have, in the simple 1D model, the ability to settle out the inert solids a little faster than the regular biological solids. That can be handy if you're seeing a significant change, for example, in your VSS to TSS ratio as you go across the primary clarifier. I've occasionally had to do that as part of a model calibration if you've got some particularly well-settling inorganic component in your incoming waste stream that you want to get rid of in the clarifier, and you can dial up the settling velocity of just the inorganic part by itself. We also have a number of other models that are simpler models that are inside our clarifiers, and in those cases, say for example the differential model, that allows you to separate things out on a state variable by state variable basis. And that is also the case, too, for our other objects that do solid separation, like the microscreens and the hydrocyclone. You can set those up so that they will separate out the inorganic things, like the precipitates, in a different way than, or at a different efficiency than you would find with the regular biological stuff. Okay, so that's in terms of like the precipitates and doing that solid separation unit. Moving on to things that specific unit processes that deal with pH control and so on. We of course have a couple of units that are available in the influent tab. You know, farther down the list, after you've got your regular wastewater influent and the truck influent, you'll find a bunch of chemical influents as well. And these things also play a role in controlling the pH and controlling the precipitation of precipitates in your plant. And so these are relevant here, the acid dosage and alkali dosage units. These are where you can add chemicals to your process. And so if I just open up the alkali dosage menu here, you can see you can select from which kind of chemical that you want and specify its strength and so on. And then the flow rate menu, you specify how much you're adding. So quite frequently we see these used in concert with, say, the struvite recovery to control the pH, and maybe you're also doing some sort of dosage of other elements there. So if you need ions, if you're short on magnesium or something, you can do that from here too. Another one that's a sort of semi-equivalent thing, but is actually an inline unit, is the inline chemical dosage. And this is the one that is typically used for adding alum or ferric chloride or ferrous sulfate for doing chemical phosphorus removal. And so this is yet another example of a place where we're doing chemical units, chemical reactions that are going on that are separate from the biological ones. So here, it's happening in a unit that's not a biological unit. And we're assuming in this case that all of the equations and the reactions that are there are going to completion in just this one unit. And in this case, you specify the chemical type that you are adding and the strength of it, and then the chemical dosage. Here, you can either do it on a mass basis or a concentration basis. And there's actually controllers can be set up on this as well. And in this case, we're doing something slightly different than we are in some of the other places, in the sense that we've calibrated this model with a model that sort of doesn't act completely stoichiometrically. It acts in a more realistic kind of way. And this graph is actually from our GPSX technical reference. There's several pages on how this model works if you want to dig into the details. But the key element that you can see here is on this axis, we're showing the concentration of the soluble component that we are trying to remove. So let's, for argument's sake, say that this is soluble orthophosphate. And then this is the axis on the required metal dose in order to remove 1 unit of that phosphorus. And so we can see when there's lots of phosphorus, we don't need that much unit of metal per unit of phosphorus removed until you get down to the very low concentrations. And then the efficiency of the metal dosage kind of drops off at the low phosphorus concentrations. And so there are settings to control the behavior of this, and we do recommend that when you're using this chemical dosage object that you do a little bit of calibration, or at least take a look at it to make sure that your numbers are there. You can control the shape of this curve and its location in order to calibrate for the particular dosage that you have. Okay. And then lastly, moving on to those units that I was discussing earlier, way back at the beginning of the webinar there, I discussed those companies that had struvite, precipitation, and recovery technologies. We do have a couple of units that are relevant to those technologies there. So this is sort of the anaerobic version, and there's an aerated version as well. These are biological reactors that are anaerobic environments. They have a recycle, and essentially they're there representing a sort of a fluidized granular bed. And we have the effluent coming off the top, and this is the pumping where you would pump away and collect the precipitated solids. And so I'm going to show you an example of that in my demonstration on my desktop in a little bit. Okay, so that's sort of a description of all of the things that are sort of available for you to take advantage of in GPSX. And now I want to spend a little time talking about how we go about modeling the pH and modeling the precipitation processes, since those two things are so closely tied together. Okay, so there's a lot going on in a wastewater model, which is, that's for sure. There are, as you know, probably, I think there's about 65 state variables in each one of the reactors that you have on your Mantis 2 model layout. And we have all of those organic and inorganic components that are coming through, and all of these reactions going on. Each one of those reactions, not every single one, but most of them, they actually consume or release some inorganic material as the biomass, all those 10 different biomass types, as they grow and as they decay. So they're, consuming up a little bit of the inorganics and releasing a little bit back when they die. And then on top of that, at the same time, we also have all of those precipitation and redissolution processes as it's forming the precipitate and then allowing it to come back into solution again if the conditions are right. We have the speciation calculations for those particular species that do dissociate, so anything that's sort of a weak acid or base. We need to keep track of all of that, because the important part is that we need to know what the charge is, or what are the concentrations of all those ionic species, so that we can do a charge balance, and that allows us to calculate the pH going all the way through the system. And of course, then the pH then affects the speciation, and it kind of all goes around in a bit of an iterative fashion. So many of these processes are dependent upon each other, and also other external factors like temperature. So all of the dissociation constants, for example, are a function of temperature. So the biomass structure in Mantis 2, it does, as I mentioned, allow for uptake and release of the inorganic species. We do have the formation of storage compounds like polyphosphate, and it has its own stoichiometry and uptake and so on. And then anything that's a precipitate like struvite, we've worked out, and we have, of course, the stoichiometry required to form those things as well. And just like when you're growing biomass, you need all of those components. I need oxygen and substrate and alkalinity and all that in order to be able for growth to happen. The same thing happens for the precipitation. I need every one of those elemental components, and I need them in a certain mixture in order for that precipitation to go forward. So when I run out of one of those things, then I obviously can't precipitate any further. So a key element of doing that is to be able to understand where the pH is, because the solubility of some of those precipitates depends on pH. So all of these weak acids and bases, we also have to calculate all of their charged species. And as I mentioned, the dissociation constants are temperature dependent. And so once we know what all of these things are, we can then do a charge balance to determine what the pH is. And of course, that, as I mentioned, is dependent upon itself. We do the pH model in such a way that it allows us to take the charge balance and then use the pH calculations to figure out what the pH would be that causes this thing to balance properly. And that's how we come to evaluate all of the individual concentrations of all the charged species. So for many of these things, like this one for ammonia, for example, allows us to write a regular equilibrium relationship here, and we have our equilibrium constant. That does allow us to rearrange that equation into a way that says I can calculate what my charged species concentration is as a function of pH. So we can do that for actually all of the dissociating state variables in the Mantis-2 model, of which I think there's 7 or 8. And so things like ammonia, obviously, as I'm showing here, but we have acetic acid and propionate, and then of course the carbonate system as well needs to also be dissociated. So what that does is it allows us to sort of write an electroneutrality or charge balance equation that is a function of H+, is a function of what the pH is. So all charges associated with those ionic species basically must sum up to 0. That's what the definition of electroneutrality is. So knowing that that has to be true, we can then write everything in their total concentrations and then use the speciation equations to find what their charged versions are, and then sum all of those up, all of the positive ones and all of the negative ones, and then solve for the pH that gives us a charge equal to 0. So just to write that out in sort of an equation kind of format, we have all of the positively charged ones on the left and all the negatively charged ones on the right. And these cations, it depends on which one of our libraries that you are using, but I'm going to show you mostly the ones here for the Mantis-2 model. So here they would be, making up things like sodium and potassium, calcium, magnesium, and so on, and any of the other ones that are speciating that have a positive charge, like ammonium here. And then the anions are all the negatively charged ones, which includes things too, like there's, multiple charges on the phosphates here, so you have to include all of those. And then also the dissociation of water. Now, any place where we have something like this, we can actually write it. If you remember from the previous slide, I can actually write that as a function of H+. So what we do is we then insert any place that we have something like this with the version that is dependent on H+. And so we would do that for all of these. Then we'd write all the positive ones on the left and substitute everything in the top here, all the negative ones on the right. And then everything, the only unknown left at that point to solve for is H+. And so we do that, and then basically we've solved the equation, and we now know the pH. And then we can actually substitute it back into all of these equations to calculate their charged form as well. So that's how we come up with the pH. We do a big charge balance across every place you see a reactor, and even in the biofilm units, at every biofilm layer, we do it as well. We're doing this kind of thing where we do a charge balance and then we solve for the pH. Once the pH is known, basically we can calculate all of those ionic forms, and then we can calculate things like the various forms of alkalinity, because we now know all of the charge concentrations and the acid neutralizing capabilities thereof. So any and all of this stuff can be plotted in GPSX by right-clicking on, say, this tank here, going to the output variables, and then going to pH and alkalinity. And that's where you'll find a large menu that has the pH, the alkalinity, and actually the concentrations of all of those ionic species are there and available for you to play around with and put on graphs and see how they react to changing operation of your plant. Okay, so that tells us how we get to the pH model and how we get a pH answer. So the other thing that is the mixture in the equation here then is how do we precipitate out all of these things? What equations are we using there? So you can see here, for example, these 8 or 9 precipitates here. I picked an example where we were precipitating out some struvite here when I took this screenshot earlier yesterday. We are using this kind of approach here. This is a dynamic rate that exists right in our biological model matrix. So the rate of the struvite precipitation here, for example, is this precipitation rate constant times these concentrations here. These are the elemental concentrations, minus the solubility constant times this switching function. And what this does is this helps to drive the formation or redissolution depending on whether it's at solubility or not. So say we had not very much struvite and we had lots of its components ready to go, then this would be a large positive number and it would drive the formation of it. But if we had not very many of its components and we had lots of struvite, then it would drive it in the backwards direction and it would redissolve back into the liquid. So these are there, they're part of the whole system, they're automatically happening all the time. And there's a number of other sort of bits and pieces to this equation I'm not showing here that are related to the sensitivity of the solubility to the pH and so on, so and temperature and other things too. But nonetheless, that's kind of the rate process that is available there. Okay, so what I'm going to do then is I'm going to do a short little demonstrations of the pH model and then of the precipitation, just so that you can see what that looks like there. Okay, so here's GPSX, and this is not really a wastewater thing. This is actually purely a chemical reaction that I was going to use just to show you the details of how our pH model works. So this is adapted actually from one of the layouts in our sample menu. So you can imagine this is just a reaction with a reactor with not wastewater in it, but just a simple, very weak base solution. And I'm going to incrementally add a little bit of acid here. So basically, I'm doing a titration in this case. So I'm going to run the simulation here, and dynamically we can plot, for example, the pH here in black. And you can see here, this is basically a break point here in which the pH drops down as we were adding more acid over a period of time. So at every step along this way, we are recalculating that electroneutrality, that charge balance equation, in order to find out what the pH is that would cause that entire system to be charge balanced to zero properly. And so, of course, as we're adding more acid to that system and we're adding more anions, that causes the pH point to sort of flip over, and it moves as we've added those along in time. So if you ever want to play around with just the pH model by itself, you can come to the sample layouts menu and look under process analysis, and there's this little sort of desktop experiment, I guess you could say, bench scale lab experiment here by doing a titration. Okay, so that gives you a little feel for what that looks like. I'm going to hop over to an actual wastewater treatment plant now. Okay, so this is a little short demo here where I've got a conventional activated sludge, regular conventional system here. We're doing nitrification and so on. And we're taking the sludge, putting it through some sludge thickening and into this digester. And so what I want to show here is how struvite is going to be precipitating out in this digester. So I'm just going to run a regular steady state simulation here. And I did make a, I'll just quickly show you that this is just sort of running conventionally here. Our mixed liquor is like 2,600 and we're fully nitrifying here. 25 milligrams per liter of ammonia coming in and 0.1 coming out. So we are doing, sort of regular biological growth in this system. I think the SRT is like 8 or 9 days. And our digester is doing pretty much what it's supposed to do. 30 days of HRT there. We can see we're producing gas. It has methane of a little over 50% here, and it's doing 50% VSS destruction. So regular digester performance. So let's take a look at here. I put up this little table, which kind of shows the incoming struvite components concentration into the digester, and also the concentrations in the digester itself. So the first thing in that list is the ammonia nitrogen. You can see it's really low coming in, of course, because we were fully nitrifying in our plant. But then, of course, in the digester, when it undergoes the digestion process, of course, it's releasing a lot of nitrogen back into the system through the death of those cells and so on. Also releasing back a lot of phosphorus here. So we now have high concentrations of phosphorus and nitrogen and in that format. And then I also plotted magnesium. That's the third component required to precipitate out struvite. So, and we can see it was 50 coming in. That's pretty much exactly what it was coming in the influent. And now it's only 0.1 coming out. That's because we're precipitating out a fair bit of magnesium ammonium phosphate, or struvite here. We can see 1,250 milligrams per liter of that is being precipitated in the digester itself. Now, in reality, of course, that would stick to the walls or collect on the bottom of the digester or what have you. in GPSX, it is a particulate component of the contents of the digester itself. So if you pump something out of the digester, it's going to have this concentration in it. You could then put another solid separation unit after it here in order to simulate the process of having it settle out, and or something like that. Whatever is appropriate for your particular situation. So this model, of course, is sensitive to changes, and I'm going to actually change the excuse me, influent characterization here. I'm going to knock that soluble magnesium down a fair bit, because it is actually the rate limiting step in the process here, because it seems to run out of magnesium before it runs out of anything else. So when I do knock that down, we can see now it does actually produce less struvite here, because we don't have enough magnesium to go with all of the excess ammonia and phosphorus that we have kicking around. So you can see that that is automatically a standard part of the model. You don't need to do anything special to set up struvite precipitation. It's automatically going to happen in the places where it is relevant and where the conditions lead to it in the model. And I'll just show you really quickly where some of those kinetic parameters are. If I go here, go to the kinetic menu, and this is where we have the growth rates and half saturation coefficients for all the different biomass types. Most of the precipitation stuff's near the end, so I'm going to skip way down here. And then you can see after we get past all the biomass stuff, we can now get to precipitation of calcium carbonate and struvite and nuberite and so on. These are those rate coefficients that I described earlier in the equation in the slides. Here, precipitation rate and dissolution rate, and then we also have the solubility product there, and then that switching coefficient. So these are coefficients that you can use to actually calculate and calibrate, if necessary, the model to do the precipitation in the way that is the most realistic for your situation. Okay, on to the last one. Since we have a nice setup already in place, I did want to highlight the struvite precipitation and recovery reactor. This is the anaerobic one. These are found in the biosolids treatment panel here. There they are right there. So this is a conventional activated sludge plant. We're thickening the sludge through the digester, and then we're picking up the return liquors here after it's gone through dewatering. So these are very high concentrations, low flow rate coming here, and being mixed with some magnesium dosage and some acid here to do pH control. And so we're getting that coming in here into that reactor. And then from the reactor, we can then take away the liquid, but after we've presumably precipitated out all that struvite, it then goes off to this fertilizer collection. So let's just run that. This again is actually an example from our sample layouts. Again, if you go to the side stream processes section of our sample layouts menu, which is here, file, sample layouts right there, and then you can see the results. Okay, so now that's converged, and I'll just very quickly point out that this unit has the flow coming in, and again, as I mentioned, it's a bit like a fluidized bed. We have some information in the model about the size of the unit and some of the details about the reactor itself. There is a solid separation element to this here, so you can see that we do have some questions that we ask about the nature of the granules that are there, the size of their end, and we use this to determine how well the solid separation is happening. So then all of that, those solids that precipitate out are then collected into this pump connection point here. So I will just point out that if I scroll down here a little bit, we can see struvite is one of the things that we can plot. And yes, indeed, we are producing a very large, very concentrated form of the precipitate here in this pump connection point right there. So that's another one you could play around. You could see how sensitive it is to the pH and sensitive to the magnesium concentration. Again, like the other example I was showing, sometimes you have to make sure you have enough magnesium to get rid of all of the excess ammonia and phosphorus that are there. And then you can do that within this model and within this unit processes. Okay, so let me go back to my slides. Okay, so that kind of covers all the things I wanted to say basically about the pH model and about the inorganic precipitation. It's a complex relationship between those two things, and of course they're completely ingrained into what's going on in the biological part of as well. The pH solver itself, the pH calculation can be turned off if it is causing convergence problems. And by convergence problems, I mean when you hit the steady state, if it kind of like does not come all the way across to steady state, or it keeps starting over again trying to get to a new answer, it takes a long time to get there. If you don't care about the pH, if that's not the important thing that you're trying to do, you can actually just set the pH to a specific value. And not bother solving for it. So you go up to the top left-hand corner of your drawing board, click on the Site Properties menu right here, this little pin, and then in the biological models setting area there, you can switch from estimate pH over to set pH, and then it'll ask you what pH you want to set, and so put 7 or 6.5 or whatever is appropriate, and then it shuts off the actual part of the calculation. It makes the model a little less bouncy, and then therefore it can get to steady state faster. We also have a pH inhibition function that is applied to all biological growth. Right now, there are some elements, certain individual biomass types that are inhibited by a particular ionic form of the elements there. So you can have acetic acid can be inhibited, but only at certain pHs. But this is a sort of an overriding version of all of that can be applied to all the biomass types evenly. Now, we have this turned off by default, but basically it's a pH inhibition function where you set the sort of the corners of this thing. I want to say in between, say 6.5 and 8 here, that the pH, there is no pH inhibition. This is a 1. We multiply the growth rate by this number, so no effect. But if I get down here and I'm down at 6, then it's only going to be running at, say, half speed. Or if I get all the way up to 10, it's only going to be running at half speed. If I manage to get all the way down to 4, then basically that would turn the growth off altogether. This is actually turned off by default, but you can come into, again, that same spot, go on the drawing board, and the pin in the upper left-hand corner, and then go to biological model settings, and then under apply pH correction, switch that over to yes, and then that will be part of the model as well. Okay, so just about right on time here. Got leaving 10, 15 minutes for questions. A few final thoughts here. The Mantis 2 model basically has a very sophisticated approach to doing the water chemistry. And it's a really powerful tool to be able to assess the effects of the biological growth and the chemical makeup of that influent and the chemical reactions that are present within your wastewater treatment plant, what effects those have on pH and what effect the pH has on them. As I mentioned, it's sort of that interrelationship there. You can simulate the formation of struvite and many other precipitates all the way through your facility. It requires some information on the concentrations of the ions in the influent. And so, for example, it needs to know some details about what is your influent magnesium concentration. And there are some extra pH inhibition functions available for you to use them if you are in a situation where you feel that that is relevant. They're turned off by default, but you can just pop in there and turn them on when you want to. Okay. All right. So what I want to do is just have a few words here about some things that are coming up at Hatch. So can you, if you would like to ask any questions about today's presentation, or indeed anything at all about GPSX, I would be happy to stick around at the end of the presentation and answer those. So the first thing you need to know, if you haven't heard already, is that a few months ago we released a new version of GPSX, version 8.1. That was what I was just showing you earlier today. And the easiest way for you to get that is to go and start up your copy of GPSX, go to the Help menu, go to Check for Updates. And if you are using a version that is less than 8.1, it will pop up this message, and it has the link where you go. Just click on this download link here, and it will take you to the part of our website that will get you their newest version. If you are unsure whether you have a license to get upgraded to the newer version or not, just please send us an email and we'll help you out. So you can send it to support@hydromantis.com, and then that will find its way to us. Some of the things that you'll find new in version 8.1 is there's, of course, as always, updates to our models. We have a new chemical disinfection model. So previously, the dosage model was simpler than the one that we have now. We added for the chlorine dosage there some effects from nitrite consumption and a few other things. We added a new dechlorination model part to that part of the GPSX model, and we updated the disinfection model as well. We have a new primary clarifier empirical differential model. So that's the simpler model that I mentioned earlier, where you can make the inorganic parts settle out faster if you like. And we did a fairly significant update to the high purity oxygen to HPO output displays. If you are a user of our water process library, we have a new unit there for flocculation. And also we updated the Mantis 2, Mantis 2S, and Mantis 3 calibration of the model. In fact, changed a few of the equations a little bit as well for PAO storage and growth, and changed up a few of the hydrolysis rates for the slowly biodegradable COD as well. So as always, we tend to touch up the calibration every time we release a new version, just to keep it working smoothly based on our experience with using it in our own projects. Our next webinar will be on optimizing nitrification and denitrification. And I'm going to be covering in the first part of the webinar how we model those things. So it's basically a standard review of the Mantis 2 model in terms of the biomass types that handle nite and denite. And then in the second half of the webinar, I'm going to go through the process of doing optimizing, how you would optimize that, particularly on the denitrification side, since there's kind of a lot of moving parts there. And I'm hoping to get into doing a little bit of automated sensitivity analysis and optimization to try and hit on some of the interesting things. I think what we'll do is going to set up a challenge question for ourselves, and then tackle it, trying to get the denitrification to be the best shape that it can be. So that'll be on Thursday, July the 15th at 2 p.m. Eastern. You can go to our website right now and go up on the events tab and find your way there to the webinars, and you can register for that. And we all, as always, send out an email a couple of weeks before asking you to register for that. Okay, so if you have any other questions that pop into your mind, you can type them in the questions box now, or you can email them to me, spencer.snowling@hatch.com.